Hello everyone, Aaron here. Welcome back to Leetcode. Today we are doing the Palindrome Linked List problem. Diving right in, the definition says, given the head of a singly linked list, return true if it is a palindrome. So 1221 is a palindrome because if we read it backwards, 1221. 12 is not a palindrome because if we read it backwards, 21, not the same thing. So there's lots of ways to tackle this. One way is to write an indexing function and say, well, is the thing at position 0 the same as the thing at the end? 1, end minus 1, and so on and so forth until you meet in the middle. That's horribly slow because indexing into a linked list is horribly slow. One better way is to reverse the linked list, which can be done in order n time. And then then you just run through both versions, the forward version and the reversed version, and if they're exactly the same, then you know it's a palindrome. That does copy the whole list, so it uses order n extra space. This was order n speed. If we were to do the indexing version to index into something as order n, and we need to do that up to n times, so that's an n squared algorithm, which is quite slow. I noticed down here there's a challenge which says, can you do an order n time? Which we can do, but only order 1 space, which means we're not allowed to copy the list. And now, I have an idea for this, and it cheats a little bit, because it uses order n space only on the stack. So it does it recursively. I don't know if that counts because I can't think of a way that would preserve I can't think of a way to do it in order 1 space without doing that cheat. But I think it's workable. Let's give it a go. So the approach I'm going to take here is I'm going to leave something at the front. I'm going to dig all the way to the end, and then I'm going to start walking back, unwinding the stack I've just done, while walking the second head pointer forwards. So it doesn't allocate any extra memory, it doesn't create a copy of this linked list or anything like that, but it does use the stack frames to implicitly hold the information. And I'm going to need n stack frames because I'm going to do n recursive calls. So kind of cheating, kind of not. And then what I want to do is, I don't actually know how I want to check this yet. Bool is palindrome equals true. And then what I want to do is I want to call, its return is palindrome. And what I want to do is have this function that digs down and then winds back up while stepping the head down on the wind up. So I want to dig down on the head, giving it head 2, the address of head 2, this is a pointer, a pointer to a linked list, a pointer to the head of the linked list, and I also want to give it the address of is palindrome. So it's going to dig all the way to the end, and then when it's coming back up, it's going to start moving the head down as it goes. So void dig down. This is going to take a struct list node head struct list node star head 2 pointer bool star is palindrome pointer. So if head equals null, return. We're done. We've dug all the way to the bottom. We don't need to check anything at this point. Else, what we want to do is we want to dig down on head next. Still with head to pointer, and it is palindrome pointer. We haven't manipulated any of that yet. Once we've dug down, this is where we need to do the check. Let's say we reach the bottom, we return null. Now we've fallen back up here. What we want to do is we want to check if head val is equal to head 2 pointers value. In this case, that's good. In fact, we want to do more of a not check here. Sure if there's a way to break out its early. I don't think there is. In fact, yeah, no, that's something we want to check. If is if the value at is palindrome is false, return. Give up. We can stop checking. However, if we're still worth checking, we then want to say, well, is the thing I'm looking at, this one in this case, equal to the thing that I'm looking at here? If it isn't, set is palindrome to false. In fact, no, let's do this later. If it is, you want to do something leave is palindrome. Oops. It's palindrome. If I want to leave the value as true, and what I want to do is I want to say the value at head 2 pointer is equal to the value at head 2 pointer next. So this thing is going to step down, and I'm going to return. And then here I'm going to return. So here I basically said return in every case, which I don't need to. But whatever. So let's think about this here. So I'm looking at the head is 1. No, head is pointing at the 1. Head 2 is also pointing at the 1, and his palindrome is currently true. I go in here. Is the head null? No, it's not. Then I want to dig down with the next thing, leaving the head 2 and the palindrome palindrome unchanged. Then I go here. Is it null? No. Is it null? Yes, it is. Great. I go here. Is palindrome p is equal to false? No, it's not. It's still true. So I'm going to check, is this thing equal to this thing? If it is, I want to move this thing along, this head 2 along, and I'm going to return, which is going to pop me back up to here. So this one here, is palindrome is still true. So is this thing equal to this thing? Yes, it is. Actually, I can do another check here. If head is equal to the value of head 2 pointer, Oops, I need to do that after this though. If we're on our way back up and head is equal to the head 2 pointer, then we can stop looking, basically. I want to get rid of some of these returns. I'll turn this into a do nothing. So this is going to be else if. This is also going to be an else if. Don't need these return. Don't need this return. This is going to be a do nothing. So this is more of a, if head does not equal null, then that's the case where we actually want to do something. Both of these cases are null, so if head, if we've met in the middle, or is palindrome, we have already decided it's not a palindrome, do nothing. Else if head val is, if the thing I'm looking at is the same as its pair, then we're done. In fact, this is going to be quite rare, isn't it? This is only going to happen on a perfect meet, so here these are going to swap positions. What it's going to be is if I step back, oh whatever, if we do the whole list, we do the whole list. It's not the end of the world. If we walk all the way back up and all the way back down, I don't really care. It's still order n. It's just doing a little bit more work than it really needs to. It's just working out if they've passed is quite complicated. Right, let's give it a test. I probably made a mistake anyway, so let's knock out some bugs. That one worked. Let's use all the test cases. Ran too soon. Run code. So again, this one's kind of order 1 extra memory, and these are the only things I allocate, but it's kind of order n in the fact that this is a recursive function. Yeah, it is what it is. Let's submit it, see how we did. Nice. Completion 2 days. 2 days straight. So we see we were faster than 41% of submissions and used less memory than only 11%, so we were not terribly efficient by any means, actually. Probably a bit of a factor is that, well, the speed, we're probably not checking for the, well, we know we're not checking for whether we crossed or not, so that's not great. And the memory usage here is probably because our stack frame is larger than a linked list node. So although I've sort of done the trade-off here of using stack frames rather than copying the linked list, I've paid for it because stack frames are bigger. It was a fun challenge nonetheless to see if we could cajole it down to this order 1 memory. That's going to be it for today. Thank you very much for watching, and I will see you all next time. Bye.